Hi, welcome to Concept Based. I'm John Hepworth, and we are in the Year 11 Advanced content in Introduction to Differentiation, and we're looking at doing calculations with derivatives. Now, if you haven't watched any of the previous videos in this section, I'd recommend going to them if you're new to calculus and new to doing derivatives, because there's a couple of videos that really explain essentially by first principles or by limits how it is that derivatives actually occur. And I'm going to make reference to those videos at the start of this video, so if you haven't seen them, definitely check them out. The reference that I'm going to make is that before we look at this question, find the derivative of f of x equals x cubed plus 2x plus 1, is that when we were doing the limits, we looked at, well, what happens if we took the derivative of x squared? And we found that the derivative function was equal to 2x. Similarly, if we took the derivative of y equals x cubed, we found that the derivative was equal to 3x squared. And it's from these explorations that we should come to the realization that there's a pattern that's forming here. We can see in the cases that we were doing where possibly you might have used the Desmos calculator that I'd created for looking at those limits, was that the power of the function, so x squared, dropped by 1, we ended up with an x, and the power that was there ended up multiplying out the front. So x squared became 2x, x cubed became 3x squared. And this realization leads to a rule. And so that rule is in your syllabus. And the rule is stated that if y equals x to the n, then the derivative of that equals n x to the n minus 1. And so this is really the fundamental rule that you'll be using in calculus for most of your questions. Now, don't get me wrong, some derivatives in the future get much harder. There's trigonometric derivatives, there's exponential derivatives, and they all sort of have their own different rules. But the fundamental rule that we're looking at is this one, that we need to take the power at the top, multiply it out the front, and then drop that power by 1. So let's go ahead and apply this rule to this derivative function, or to this function that we have here, and find its derivative. But before I do that, there is actually a second part. What I want to note here is that this x cubed really is a function on its own. And this 2x is also a function on its own, as is this 1. And the question is, well, even though we knew that x cubed became 3x squared, what about when they're all put together? And it turns out that if there's just a summation of different functions, then the derivative of that is just the derivative of each function still summed together. So you can go ahead when there's a sum there and just do the derivative straight through. If it was something different like this, like f of x equals x cubed times, let's say, x squared, although we can simplify that and then deal with it, if we had some sort of multiplying thing in the middle of it, that creates a whole nother rule, which I will look at in a future video. So that's not what we're talking about. We're talking about when these are separated by an addition or a subtraction. Of course, the subtraction is exactly like the addition, because really it's an addition of -1 lots of that function. That's what the subtraction actually is. So that being the case, let's follow this rule and find the derivative of this function. So the derivative of f of x in this case, so we take our x cubed, we multiply the power out the front, and then we drop the power by 1. So 3 minus 1 is 2. We then have 2x. So now there is already something out the front. What does that mean? Well, if you're multiplying your function by a constant, in this case 2 lots of a function, you just differentiate the function like you normally would in the rule and just leave that multiple out the front. So we're going to essentially be differentiating x to the power of 1, which means we would bring the 1 down the front and then raise the power, drop the power to 0, and x to, I might do it all step by step. So there's multiple out the front staying there. We're going to bring the power of the x out the front, so it's a 1, and then x gets dropped by 1 power, and we end up with a 0 here. So with that being the case, we need to realize that multiplying by 1 does nothing, it stays the same, and x to the power of 0 is 1. So when we do the derivative of 2x, we just get an answer of 2. Now, side note, that makes sense because if we looked at a function y equals 2x, essentially what it's doing is it has a gradient of 2 over 1 at all times. So the gradient always along this line everywhere is going to be 2 up, 1 run, 2 up, 1 run. So that gradient of that straight line becomes constant, and it's a 2, which is what we see here. Now, the next one I could do using the rule, but I'd rather you have a conceptual understanding of what's happened here because we're in concept-based right now. So let's think of what 1 looks like as a function. It looks like a line, right? That's what a constant will graph. So that's going through at 1. And so whenever we're finding these derivatives, we're looking for the gradient at a point. Now, the gradient on the point y equals 1 everywhere is the same gradient, and when something is flat, it has a gradient of 0 because it doesn't rise. Rise is 0 over run of anything is going to be 0. So we just have a 0 gradient everywhere. And that makes sense if you want to consider the rule, because if we were considering the rule here, I suppose we could consider this as 1x to the 0. And if we then multiply by the front by 0, 0 lots of anything is 0, so we end up with nothing. So we could say add 0, but we don't do that. We just know that adding 0 doesn't change anything, and we end up with the derivative function being 3x squared plus 2. So we can apply this same methodology to anything where it's a sum of functions where those functions are just functions of x raised to a particular power. If x was raised to a negative power, we can still just treat it exactly the same, multiply by the negative power at the front, drop that negative power by another 1, and it would become an even lower power of x. And so you can just go and apply this to all sorts of functions where it's just a sum of different functions where it's x raised to a power.